Have you ever wanted to make a movement system like in Baldur's Gate 3? Well, in this video, I'll be showing you how to do just that. This tutorial will cover point and click movement, rotating the camera with keybinds, rotating the camera by holding the middle mouse button, moving the camera freely while maintaining point and click movement, and recentering the camera on the player. Just a quick disclaimer that I do not claim to be a pro, and if there's anything in this video that you would do differently or optimize better, let me know in the comments so that others can have the best result possible. What you'll want to do first is create a 3D scene in your Godot project. This will be the test area we'll be working with. If you already have a world you've made, then feel free to use that instead. For the ground, I'll be creating a CSG box and positioning it so that it looks like a nice big ground. I'm adding a material and making the ground a nice deep blue color just to make sure I'm not seeing too much white on white action. I'll be renaming the CSG box to ground and save it as main. If this isn't the main scene for you, then feel free to save the scene as whatever you want, wherever you want in your file structure. With our ground created, we'll now want to create a player body. To do this, we'll create a new scene and change the root node to character body 3D. We'll rename the root node to player, and then we'll create a new mesh instance 3D. Once we add the capsule, we'll hold Control and move it up so that the bottom is flush with the axes. I'll rename that to Mesh. Then we'll want a collision shape 3D and make that a capsule as well. And do the same thing so that it perfectly engulfs the mesh. Next, we'll need a navigation agent 3D so that we'll be able to get the player to navigate to our desired spots. I'll rename that to navigation agent. And you'll just want to save the scene as player. Now that our player body is created, it's time to create the player camera. Let's make a new scene, and make the root node a character body 3D just like last time. The root node will be the point of the ground in which our camera will always be facing, so let's call it ground point. We'll want to add a collision shape so that way it can stay on the ground and not fall through it. The collision shape can be anything you want as long as it's small, but let's make it a sphere. We'll also make it flush with the ground so that it won't fall through the ground when placed. Now we'll add another character body 3D to the first one, which may seem redundant, but there's a reason for it. We can name it Camera, and we'll want to add a camera 3D inside of the inner character body, named Camera. I accidentally named them the same thing when I was recording this for the first time. You'll typically want to avoid this, but this shouldn't cause an issue in our circumstance. Next, you want to give the camera some collision, and you can do so just by copy and pasting it from the ground point. Now you'll want to select the inner character body 3D, and hold Control and move it back about 5 units, and then up about 5 units. You can eyeball it or play around with it to see what distance you like, but I found that 5 and 5 works for me. This is going to be the distance that your camera starts at from the ground point. Next, you'll just want to save this one as player camera. With all that done, you can finally add the player body and the camera to the scene. It doesn't matter where you place the camera, as we'll be centering it on the body in code later. And when we go to test it, I realized just how bad it looks without a sky and sun, so pardon me while I add that real quick, and feel free to do the same. Much better. To create the movement keybinds, click Project in the top left, then click Project Settings. Then we'll click on the Input Map tab at the top, and in the search bar that says Add New Action, type in the movement directions. We have forward, back, left, and right. Now just click on the plus sign next to each of them and bind them to your desired keys. For me, and probably all of you, it'll be W, A, S, and D. Then click Close. Now for the fun part, the actual coding. So the first thing we're going to do is make W, A, S, and D move the camera laterally. So, first, we'll want to go into our camera scene and add a script to the root node ground point. Now we'll add a camera body as an onReady variable. An easy way to do that is to just click and drag the camera node into the script and hold Control and release it. Next, we'll want to create a variable called attached_to_player, which will start out as true since we want the camera to start attached to the player. Then we'll create a variable called speed and set it to whatever speed you want. I'm doing 5.0. Next, we'll make a new function and call it moveCamera. This will take in the delta parameter. Now, for those of you who don't know what the delta parameter is, or parameters in general, or don't know and don't care, feel free to skip to the next part of the video. Video skip points are in the description and in the timeline. Oh, you're still here? Well, if you don't know this, good luck with the rest of the video. A parameter is a value that's placed at the start of a function, and all other values in that function will be the same as that value. This is especially important with functions that are called every frame, just like the one we're about to make, because the parameter we put here, which is called delta, and the value that it will be given is the time passed since the last frame. This is how we make everything move over the course of time in the Godot engine. Now that we're in the function, we'll make a new variable for the input direction, input dir, and we'll get the vector for left, right, forward, and back corresponding to our WAS and D keys. Then we'll check if the player is trying to move by saying that if input direction does not equal vector2.0, which essentially means that if no keys are being pressed, the following will happen. First, since the camera detaches from the player body when any movement key is pressed, attached to player will become false. Now we'll create two variables for the forward and right direction. And you might be wondering where's the backwards and left? Well, that'll come later. They'll be both the Z and X axis respectively. And we'll make both of them normalized by calling the normalize function so that the length stays consistent. Now we'll create a variable for the move direction, and this will combine the forward and right direction based on the player's input. If the player pressed W, then the forward direction is multiplied by 1, which will move forward. And if the player pressed S, then the direction will be multiplied by -1, which will make the player move backwards. Same thing with the right and left direction. Next, we'll want to set the velocity to the movement direction times the speed, which is set to 5. Then below that, we'll want to take the camera's global transform origin and add velocity times delta. And that function is complete. Now we'll type out Godot's built-in function called physicsProcess. This is the process that's called every frame. Inside of physicsProcess, we'll call the function we just made and pass in the delta parameter from this physicsProcess parameter. And below that, we'll also call another method called moveAndSlide. This method will actually enable our camera to move around the map. Now if we go ahead and run our project, you'll notice that pressing the movement keys will move it in the correct direction. But when we release the key, it'll continue going in that direction no matter what. We could just make the camera stop immediately, but in Baldur's Gate, the camera kind of slows to a halt in a nice smooth manner, so let's replicate that. Back in our script, let's make a new constant called damping factor, which is basically our deceleration speed. Let's go below our move camera function and make a new function called apply damping. It'll pass in the delta parameter as well. And inside the function, we'll set velocity x to the move towards method, which takes in the starting velocity, the ending velocity, which we want to be 0, and how quickly it slows down, which will be our damping factor times delta. And let's do the same thing with velocity z. And that's the end of that function. Now let's head back into our move camera function and add an else statement after our big if statement, and just call our apply damping method we just made. This will tell the game that if we aren't pressing any keys, slow down the camera to a stop at the deceleration rate of the damping factor. Now if we load up our project again, we'll see that the camera will slow to a halt after we release the buttons. And with that, lateral movement is done. With that out of the way, let's tackle rotating the camera with keybinds. Like we did with our other keybinds, we'll click Project, Project Settings, Input Map, and create two more inputs called Rotate Left and Rotate Right. Baldur's Gate has them bound to Q and E, so I'll do the same. Now that the keybinds have been made, it's time to write the methods. We'll handle the camera rotation in two methods. One of them will handle the actual technical rotation of the camera around the root, while the other will handle the keybind pressing to call the rotation method. Let's start with the technical rotation method. We'll call it rotate camera around root, and give it an angle parameter. Then inside the method we'll create a variable called toCamera, which will be the distance from the root node to the floating camera. Now we'll create a variable called rotation, which will be the rotation matrix. In this variable we'll use a basis with vector3 up and the angle parameter. Vector3 up will ensure that the camera consistently stays rotating around the y-axis, and the angle will be the amount of rotation applied around the axis. Now we'll take the toCamera and apply the rotation matrix to it, effectively rotating it by the given angle around the y-axis. And finally, we'll change the camera's position accordingly, by taking the root position and adding the new camera position. For the sake of clarity, I'll collapse the other methods real quick. Let's create a new constant at the top, which will be the rotation speed. As the name suggests, this will be the speed in which the camera will rotate. I'll make it a 1, but you can make it whichever you want. This next method we're making, handle camera rotation, will be much easier than the rotation method itself. We'll pass in delta since we want to call this every frame, and then we'll give it some if statements if the buttons are pressed. If input.isActionPressed is our rotate left keybind, then call the rotation method we just made with the parameters negative rotation speed times delta. Then we'll do the same with our rotate right keybind, but make sure the rotation speed is positive. And finally, we'll go back into our physics process method and call the handle camera rotation right below the move camera method. Let's go ahead and test it. So you'll notice something slightly wrong here. The camera's rotating while I hold the keybind, but it's still facing the same direction. This means that I forgot a step. Why didn't you remind me? We simply have to add one line to our physics process method. We'll say camera.lookAt self.globaltransform.origin. Since this is called every frame, this ensures that the camera will always be looking at the ground point. Let's try this again. Gonna move the camera, and now we are rotating it correctly around the ground point. And now I'm noticing that the camera is a little too close to the ground, so I'll go back into the camera scene and bring it out a little more. We can, of course, fix this with the zoom function we'll be adding, but this will be the default camera position. Much better. Speaking of the zoom function, we'll be adding that next. Let's add the proper keybinds for it. You already know the drill by now. Head into your project's input map, and then add the zoom in and zoom out keybind, and bind them to mouse wheel up and mouse wheel down respectively. Now we'll want to create a constant zoom speed, and set it to a very high number like 200. I don't know why this speed requires a super high number to work correctly, but it just does. Then we'll want to set a variable called zoom velocity. The reason this isn't a const like zoom speed is because it'll be changing constantly when it's ran. Like the rotate function, we'll need two functions for zooming in and out. First, we'll want to create a function called handleZoom, which will just take the parameter delta again. And inside of it, we'll want to handle the input. If input is action just released, zoom in. Make sure you say released, not pressed. Then the zoom velocity will reduce at the rate of the zoom speed times delta. And we'll do the same thing with zoom out. And the velocity will increase by the same rate. Then we'll just say zoom velocity equals clamp, zoom velocity, negative zoom speed, and positive zoom speed. The clamp function makes sure that the zoom velocity will never be greater or lesser than the zoom speed. Now we'll add that to our physics process. It won't work yet, mind you, because the zoom velocity is not actually doing anything yet. So let's fix that. We can make two new constants called min zoom distance and max zoom distance. For the minimum, I made 2, and for the maximum, I made 20. And we'll make a variable called current zoom distance, and this will start at 10. This is why the default camera position matters, because setting it at 10 ideally will be the midway point between the min zoom and the max zoom distance. And if the camera starts really close to the ground already, then zooming in will get a lot closer and zooming out will get a lot farther and it'll look all janky, so make sure you pick a good camera position to start out with. So now we'll create a new function and call it apply zoom inertia. This will take the parameter delta. Then we'll take the current zoom distance and continuously add zoom velocity times delta. Then we want to clamp it so that it stays within the confines of the min and max zoom distance. Then we want to make another 2-camera variable, which will once again be the distance between the root point and the camera, normalized of course. Next, you want to set the camera's position to the corresponding position times the current zoom distance. Then we'll increment the zoom velocity to be the zoom damping constant, which we actually haven't made yet, so let's create the new constant at the top and call it zoom damping, and set it to 0.9. Then finally, to top it all off, we'll add the apply zoom inertia function right below the handle zoom function. Now when we test it, we'll be able to zoom the camera in and out. Let's take a step back and add the rotation via the middle mouse button. This one will be quicker since we already have the methods in place. First, let's call a new variable called rotating camera, which will be a boolean, and we'll start it at false. Next, we're going to want to call the built-in function in Godot called input. This function is fired off whenever any type of input is done in the engine, like moving the mouse, clicking the mouse, or tapping a key. Therefore, we'll want to check to see if the input event is an input event mouse button, and that the event button index is the middle mouse button. If so, then we change the rotating camera boolean to be the same value as event.pressed. This means that the rotating camera will be true if the middle mouse button is held, and false if it's not. Then you want to create an else if statement that checks if the event is input event mouse motion and that rotating camera is true. This is saying that if the middle mouse button is held, then rotating camera will be true. And if the rotating camera is true and the mouse is moved, then we'll do the following. We'll create a variable called rotation delta and make that event.relative times the mouse rotation speed, which I actually forgot to add, so we'll head to the top and make the mouse rotation speed constant and set it to 0.005. Now if you have a universal variable for your mouse sensitivity, if you're doing that with your game, then feel free to add that instead. And for those wondering, event.relative is the mouse position relative to the previous position that it was in the last frame, so multiplying it by the mouse rotation speed will give us a nice distance to rotate it by every frame depending on the mouse sensitivity. Speaking of, we'll want to call the method that we previously made, rotate camera around root, and in the parameter, we'll call negative rotation delta.y. And below that, we'll call the built-in function rotate_y to the negative delta rotation.x. Now going back into our engine, if we hold the middle mouse button and move the mouse around, the camera will rotate accordingly. So now our camera is 99% completed, but we still have one more function that we have to make, and that's recentering the camera on the player if we move it away. So before any coding goes on there, we'll have to do a quick thing in our main scene and any scene that you have with the camera and player. So let's go into our main scene and find our player node, right-click it, and select Access as Unique Name. We'll want to do the same thing with our camera node, and then we'll want to go back into our camera script where we just did everything, and add another constant at the top called a recenter speed and set it to 10. Now we'll create another keybind and call it recenter, and I believe Baldur's Gate has it set to the home key, so I'll do the same. Let's head to the bottom of our script and add a new function called recenter on player, which will simply have in it our attached to player variable that we created a long time ago, and we'll set it to true. Once that's done, we'll head back up to the top and create a new variable called player, which actually won't take anything immediately. We'll want to set the player when the engine is running, or else it'll yell at us and say that it doesn't exist. So we'll want to call another built-in function called ready. This is called as soon as the item attached to the script comes into existence, which is in our case the camera. Inside of the ready function, we'll say that the player is equal to getParent.getNode and pass in a string that is $player. This means that the player will be set to the parent of the camera node, which is the root node of main, and it will get the unique node player, which is why we made player node unique earlier. Now this way can be hacky, especially if you have a big scene with a lot of nested nodes, but if you want to future-proof it, you can instead make a method to find the player node rather than just hard setting it here. And while we're at it, let's make the camera node have the same global position as the player node so we can start it centered when the scene loads up. Now we'll want to go into our physics process function, and at the top we'll want to add an if statement, so that if attached to player is true, then the camera's global position equals itself, but we're going to call the lerp method and set it to the player's global position. Then in the second parameter we'll call the recenter speed times delta. What this is doing is that the global position of the camera will call the lerp method, which is essentially a transition from point A to point B at a certain speed. So point A is the camera's position, point B is the player's global position, and the speed of the transition is the recenter speed times delta. This means that if the camera's not centered on the player, it'll fling itself to the player at our chosen speed, and if it is already on the player, it'll just stay on the player. Then we just go into the input function, and add if input.isActionJustPressed recenter from our recenter keybind, then call the recenter on player method, which will just set attached to player to true, and then call all the stuff that we just did in the physics process. Now if we go to test it, I can move the camera really far away, and then press the recenter button, and the camera will recenter onto the player. And I can do it again while rotating the camera as well, and the same outcome will happen. And with that, our camera is finally done. Now to bring it all together, we can get the player body itself to move where you tell it. Firstly, we'll go into our player scene, click the root node, and create a new script for it. I'll just call it player. Once inside, we'll want to set a speed for the player. I'm just going to set it to 5. And we'll want to bring the navigation agent in as an onReady variable, so drag it over, hold Control, and release it on the line where you want to put it. So with the player, we'll want to tell it where to move, and in Baldur's Gate you do that by clicking on the ground in the spot where you want the player to move to. Because of this, we're going to want to get the 3D position on the ground wherever you click the mouse. To do this, we'll create a method and call it getMouseIntersect, and it'll take the parameter mouse position. Now, as the first variable, we'll get the current camera in the scene, which there's only one for this tutorial, so I'm going to do the hacky way of getViewport.getCamera3D, but if you're making this multiplayer, you can always substitute that for the camera of the corresponding player. Next, we'll make a variable called params. This will just be a new instance of PhysicsArrayQueryParameter3D. I'll explain what that is and what it does in a sec. Then we'll want to make params.from currentCam.projectArrayOrigin with the parameter mouse position, and we'll want to make params.to the currentCam.projectPosition with parameters mouse position and 1000. So what this is all doing is the PhysicsArrayQueryParameter3D will take parameters to create a raycast, and the purpose of the raycast, for our situation at least, is to make a ray from the camera to the ground wherever the current mouse position is, and check if that's solid ground. So, the params from is the ray's starting point at the camera, and params to will be the ground wherever the mouse is clicked. We also have the second parameter of project position to be 1000 because we want the raycast to be up to 1000 units, or at least until it hits an intersect. Next, we'll want to create a variable for the world space, which will just be getWorld3D.directSpaceState. Then we'll want to take that world space and create the result variable that will equal worldspace.intersectRay and pass in the params. Then we just return the result. This will return the 3D coordinates of wherever we click the mouse on the ground. For the sake of readability, let's collapse the getMouseIntersect function and create another variable at the top and call it mousePos. Then we'll call Godot's built-in input function and check for a certain input. In this case, we want to check if the input is an input event mouse button. If it's that, then we'll create a variable called lmbPressed. This will be a Boolean variable that'll check if the left mouse button is pressed. So we say that event button index equals the left mouse button and event.pressed. With that created, we can just check if LMB is pressed. If it is, then we create a variable intersect. This will be our getMouseIntersect method with the event.position. This means that if the left mouse button is pressed, then the raycast from the method we made will shoot out a ray from the camera to the mouse position on screen, and if it hits a solid surface, then that'll be the intersect point. Now we'll want to check if the intersect isn't null, just in case you click nothing. If intersect does indeed exist, then we set the mousePos variable to the intersect.position. Then, we'll take our player's navigation agent and set the target position to mousePos. This will make it so that wherever we click, our player's navigation agent will take over and make our clicked point the player's destination. So let's make our player body actually able to move. We'll collapse the input function and add a built-in physics process function. Then we say that if the navigation agent .isTargetReached or navigation agent .distance to target is less than 0.01, then just pass, because we don't want it to do anything since it's reached its destination. Else, create a variable called nextPoint, and make that the navigation agent .getNextPathPosition. Then create a variable direction, and make that nextPoint minus globalTransform.origin normalized. Then you'll want to set this x and z velocity to the x and z direction times speed. Then call move and slide. All of this essentially says that if the player hasn't reached their destination yet, continue walking in the direction to get to said destination. Now we're in the final stretch. Now that that's created, let's head back into our main scene's 3D view. You want to make sure your ground node has collision enabled. Then you'll want to add a new navigation region node to the main scene. And place your ground node inside of it. Then you'll want to go into the navigation mesh section of the node, click on empty, and then click on new navigation mesh. Now at the top of the 3D view, you'll see a bake navigation mesh option. Just click that, and a navigation mesh will automatically be generated. If you're using a terrain plugin, or you have some other way of creating a more detailed navigation mesh for a more detailed world, feel free to use that method instead. Now you want to head back into the camera scene and click on the camera node, and make sure that it has no collision layers active. This will make sure that the camera doesn't collide with walls. Then click on the ground point node, and ensure that it has neither collision nor collision masks. This will ensure that the player doesn't collide with the ground point. And lastly, go to your player scene, and click on the navigation agent node, and set the target desired value to the lowest value possible. This will make it so the player will get as close as possible to the destination before it's satisfied. And with that, the movement system is pretty much completed. Feel free to end the video here if you're satisfied. Otherwise, there is one more optional step, and that's the marker that appears where the player destination is. To make this, we'll create another 3D scene and add a Mesh Instance 3D. Because I'm not a modeler, I'm just going to make this a very flattened cylinder, but if you're doing this in your project, I'm sure you'll make something much more appealing. Then we'll just save it and add it to our main scene. Once it's in the main scene, we'll just move it to a place that's out of sight. Then we'll want to right-click on our marker node and click on Access as Unique Name, so we can access it in code later. Back in our player script, we'll want to create a variable at the top and call it marker. We don't want to assign anything to it just yet. We'll actually assign it in Godot's built-in ready function here, so we can make sure that it exists before we actually do assign it. So we'll want to say marker equals getParent.getParent.getNode with the string %sign marker. Be sure to change this accordingly if your node structure is different, or create a method to find your marker node if you don't want to hard-code it like this. Now we'll open the input method back up and find the line right below where mousePos is assigned, and we'll make a new line that says marker.globalPosition equals mousePos. Then head back into the physics process method, and where we said pass earlier, change that to marker.globalPosition equals vector3 0 -1 0. This will just move it back to that out of sight area we had it earlier. Now, keep in mind, this could be a hacky way to do this, especially if you have a lot of different scenes with various terrains, so feel free to change the marker's visibility instead of sending it to a hidden location. And finally, we'll just run this scene, and as you can see, the player is moving towards the marker, and the marker disappears as soon as they get to it. And that concludes the video. Congratulations.